Welcome again to GG413 Geological Data Analysis. The topic of this video is the test of Pearson's linear correlation coefficient, and this is section 2.2.6 of Wessel's notes. So you can imagine we make several measurements of two variables or a pair of data. And let's just call those variables x and y. Again, they could be anything. We could call them anything, but here we'll just refer to them as x and y. And we find they correlate. With a correlation coefficient of r. And this is Pearson's correlation coefficient. And again, it's the variance, the covariance of x and y divided by the variance of x and the variance in y. So the question is r significant? Or does it occur by pure chance? And maybe you've already come up with a situation like this where you're interested to see if two variables or data measurements are correlated. And anytime you calculate a correlation coefficient, it's going to be non-zero. I mean, it's going to have some value. And the objective here is to test whether that value is significant. So the way we do that is our knowledge of the situation in which x and y do not correlate, or they are independent. That is, they don't really they don't correlate. Then repeated samples will produce R's that cluster about 0 and have a standard deviation of S sub r. The standard deviation of the measured values of R will be equal to the square root of 1 minus R squared over n minus 2. So this is the estimate of the standard deviation we would get by sampling the population multiple times. And if that population has, in that population, x and y are truly independent. And the PDF of R will follow a t-distribution. With t defined as t is equal to r minus the mean value of r over the estimated standard deviation of r. Again, the mean value of r is 0, and the estimated standard deviation as I've written it above, and if we simplify that, we get r times the square root of n minus 2 all over the square root of 1 minus r squared. And the number of degrees of freedom, nu, is equal to the sample size minus 2. And the 2 is because we have to subtract our estimates. Well, we have to subtract for our estimates of the means of x and y in computing R, right? So we had to estimate the means when we calculated the variance of x and y. So we have to subtract 2 from the total size of the sample. So from here on out, we do a t-test. Okay? So the example given is we roll 2 dice. A blue and a red dice. And we roll it 5 times. And in the example given in Wessel's notes, the red dice was a 4 in the first roll, the blue dice was 5, and so forth. And these are unweighted dice, or they're not magnetic, so they're so they're decoupled. And so we're going to formulate the null hypothesis that the true correlation coefficient, and we'll use rho for the Greek letter for R, or the true R being the correlation coefficient over the long term. That is, if we roll the die many, many times, and so the null hypothesis is rho is equal to 0. And of course, the alternative is that rho is not equal to 0. So we calculate from our data, we have to calculate what R is, and we can consider that as our first step, and we find that R is equal to 0.66. So we need to test whether, this is, it's a positive value, it correlates positively, so we ask the question whether this is significant. And so we have to define our significance level, and that's alpha, and that's equal to 0.05. And this is a two-tailed test because we're testing whether it's equal to 0, and the correlation coefficient could be small or large, negative or positives. So alpha over 2 is equal to 0.025. And the number of degrees of freedom is 5 minus 2 is equal to 3. And the critical value of t is a symmetric function, so the critical value is t of 0.025 with 3 degrees of freedom. So the absolute value turns out to be 3.182. We can look that up in the table or use the correct MATLAB function. And we next have to calculate t from the equation I just wrote out. And the t value we get for this, for 0.66 for this number of, this sample size gives 1.5. And we find that t is less than 3.182, which is our critical value. So we cannot reject H0. Okay, so again, our t distribution for R is symmetric. And we did a two-tail test with each tail having an being alpha over 2. And we found that R was in the more probable range. So we couldn't reject the hypothesis that the long-term correlation coefficient of our two dice is equal to 0. Following that conclusion, another question we might ask is what value of R would be needed to reject the null hypothesis? And we can solve for that relatively simply. So our equation for t, our t value, was computed from this equation, r times the square root of n minus 2 all over the square root of 1 minus r squared. And if we set that t value to our critical value, 3.182, then we can solve for r and find the value of r that gives that critical value. Now, in solving for r, we'll have to square this term to get rid of the radicals, and we'll be left with a quadratic equation of r. So r could have two values, and we get plus and minus 0.88. So in order for us to reject H0, again at the 5% level, we would need a positive correlation coefficient of 0.88 or a negative correlation of minus 0.88. And that concludes our summary of how to test Pearson's linear correlation coefficient.